Welcome back to The Explainer. So today we're looking at one of the most fundamental, kind of hilarious, and absolutely crucial topics in software engineering, data encapsulation in Java. We're going to explore exactly what happens when we strip away the laws of physics and give our code, well, way too much freedom. And trust me, it gets messy, it gets fast, and it literally breaks the space-time continuum. To start, I want you to think about a pretty absurd question. Can you jam a speedometer forward with your thumb? Right? In the physical world, obviously not. You can't just reach behind the dashboard of your car, physically grab the needle, push it to 100 miles per hour, and expect the car to instantly match that speed. You're bound by physical limitations, mechanical engineering, reality itself. But in the virtual world of programming, unless we explicitly enforce those rules, there is absolutely nothing stopping us from doing exactly that. Okay, let's dive into this, because the author of our source text frames this whole concept beautifully. They noted, and I love this, trust me, I tried explaining that logic to a traffic cop once. He was not a fan of object-oriented programming. It just sets the perfect humorous tone for what we're looking at today. We're basically playing in a sandbox where the rules of reality just don't apply unless we explicitly code them into existence. Section 1. The teleporting car problem, when code violates reality. And this brilliantly illustrates the massive divide between reality and software. On one side, a real physical car has doors, it has locks, it has hard physical limits. But a newly minted unencapsulated code car, it has absolutely no doors, no windshield. It's essentially just a chassis rolling down the highway with an open invitation for any random passenger or any random piece of code to just reach over and yank the steering wheel whenever they feel like it. So let's look at the actual code that creates this terrifying open-door vehicle. Here we have a simple Java class representing our car. Notice that part right there, int speed equals 40. Because this variable is declared without the private keyword, it is left wide open to the world. It's just a default variable. And what that means is any other class, anywhere in our program, can just tamper with this state at will. Now, just a quick compilation reminder from our source text before we actually take this car out for a spin. If you compile this car.java file, you'll get your car.class bytecode file perfectly fine. But if you try to run it directly, you're going to hit a runtime error because there's no main method to actually start the execution. And as our author jokes here, if Java yells at you for this, don't take it personally. It apparently yells at them at least 50 times a day before their second coffee. Section 2. Escaping C programming trauma. Building cars safely on the heap. All right, so to actually run this, inside our new simulate car class, we write this single line, car, my car equals new car. We're using the new keyword to actually allocate memory for our car object on the heap. It's clean, it's simple, and it works perfectly behind the scenes. And for those of you tuning into this explainer who actually survived the trenches of C programming, please go ahead and take a collective deep breath. There is no malloc, there is no manual pointer arithmetic, and absolutely no middle-of-the-night panic attacks about memory leaks. Java is handling all the heavy lifting of memory management for us here. But just because our memory is safe doesn't necessarily mean our car is. Now, what's really interesting about this slide is exactly how dangerous that direct data access actually is. Because our speed variable isn't private, inside our main method, we can literally just write mycar.speed equals 150. Just think about what that means for a second. The car didn't accelerate. The engine didn't work any harder. The car just instantly teleported to 150 miles per hour. The author notes this is their dream speed when running late for class, but structurally, it is a software engineering nightmare. But wait, it gets infinitely worse. Because there is zero physical limits enforced on this integer, you could just write mycar.speed equals -50. We're no longer just breaking traffic laws here, we are fundamentally reversing the space-time continuum. In the physical world, negative speed simply doesn't exist. But in an unencapsulated Java class, the compiler just shrugs and says, sure, it's an integer, have fun. Section 3, the compiler traffic cop, enforcing the rules of the road. So clearly, we need a way to stop this madness. And the engineering fix we need is encapsulation, specifically using the private keyword. You can think of private as the ultimate digital lock. It's the exact mechanism that puts a hard, unyielding brake on outside code tampering with the internal state of your objects. So we go back to our car class and we update it. We simply add the word private right in front of our integer. Private in speed equals 0. And that's it. Our state is now fully protected. We've essentially rolled up the windows, locked the doors, and welded the hood shut. Outside classes can no longer reach in and touch mycar.speed directly. Let's see exactly what happens if that rogue simulate car class tries to pull that teleportation trick again. If we try to run car.speed equals 150 now, Java throws a massive red flag. Look at this exact compiler error. Simulate car.java, line 6, error. Speed has private access in car. Access denied. The mechanics of the language itself step right in to protect the integrity of your object's data. And I absolutely love how the source material describes this interaction. The compiler acts as a strict traffic enforcement officer, slapping your code with a ticket before it can even leave the driveway. It doesn't wait for runtime to crash your program and immediately shuts down any illegal access attempts before your code can even compile. Let's move to and see how this builds. Section 4, pedals over telekinesis, designing controlled interfaces. So how do we actually drive the car now without telekinesis? Well, we do it by providing controlled interfaces. The engineering team, that's you, provides public methods like accelerate and decelerate. These act as your gas and brake pedals. They're deliberately designed pathways that allow outside code to interact with that internal speed variable, but entirely on your terms. Let's walk through how safe and methodical this is now. Step 1. The driver, or the outside class, calls the accelerate method. Step 2. Your internal code safely adds exactly 10 to the private speed variable. And step 3, as a result, the engine doesn't blow up. The car doesn't instantly teleport to 150 miles per hour, and the space-time continuum remains completely intact. You've officially instituted the laws of physics. And of course, the driver still needs to know how fast they're going, right? We provide another controlled interface for that, public int get speed. This acts as our dashboard speedometer. It provides read-only access to the private state. You can look at the speed all you want, but you can't reach through the dashboard and change the needle yourself. So the crucial point is that by routing access strictly through public methods, we achieve 3 massive benefits. We keep the underlying data totally secure from tampering, we keep the logic incredibly clean, and most importantly, we bound our virtual cars firmly to the laws of physics that we get to define. Which leaves us with this final, somewhat philosophical thought to ponder. Software is really a blank canvas, devoid of inherent reality. The limits only exist if you are disciplined enough to build them. So if code has no inherent physical limits, what laws of physics will you choose to program today? Go out there, encapsulate your data, and write some incredibly secure code. Thanks for exploring this with me.